Well, it's 8 o'clock and we're going to make a start. So there's still people joining. So welcome to the another session of the BPHO Computational Challenge. So tonight, Dr. French is going to introduce the challenge itself. There'll be subsequent sessions in which you can ask details about it once you've kind of looked into it and given it some thought. With a slight change to plan, it's a slightly more experimental tack this evening, but that should be quite interesting. And without further ado, I think we've probably got a reasonable complement of people listening. So welcome, and over to you, Dr. French.
Right, good evening, everybody. So we're getting close to the course. So fantastic for those of you who have made all of them so far. If you're brand new, welcome to the British Physics Olympiad Computational Challenge. So tonight we're actually going to release the challenge itself. It will be on the website fairly soon, but you'll be the first people to see it. We're going to talk about the half of the session on experimental physics and sort of how you can use computers, modeling, to augment what your direct experience of reality, which is really the core of physics. So this course has been looking at how we can create computer models, and that's an important skill, absolutely. But the most fundamental one really is having this direct encounter with reality. With that sort of idea, we're going to start with this. So let me just bring up my little slinky physics. There we go. Right, so this is an example I made for the Physics Olympiad. I think this was part of one of the training sessions a few years ago. Can I just confirm you can see this all right, everybody?
Yes.
Brilliant. Yep. Right, so this is an experiment that you can do at home and armed with a computer. So what do you need? Well, you need a slinky. This is my rainbow slinky. I think it cost me all of about £3 from Amazon. You need a tape measure. This is quite a good tape measure. Other rulers are available. You need something to stick it to the desk. So I've used a copy of sort of Meissner and Meissner, Thorne and Wheeler's Gravitation, which is the most weighty book I own. That's why it's at the bottom of my my bookcase at the moment. And you can use that to hold your slinky and your ruler attached to the top of your desk. So the idea is that we are uncoiling our slinky, and we're going to try and figure out its length depending on how many coils are exposed. It turns out this is a rather interesting relationship. In fact, it's a squared relationship. So the length of your slinky actually goes as the square of the number of coils, which is quite a cool thing to imagine anyway. And then as long as you've got some space between the bottom of the slinky and the ground, the oscillation is sort of, it's like a pupa. It's a bit like, because, the coils are sort of slightly different extensions. It looks like some sort of like an insect, sort of a worm moving along the ground. But these oscillations are actually very similar in dimensional terms to that of a pendulum. So it's going to go as the square root of the length over the mass. So there we go. Over the strength of gravity. But the constant in front of it is not the same as a pendulum. So basically all you need is a watch. I've used my smartphone here. Any other stopwatch will do. A slinky, a ruler, and something to hold it on the desk. So let's go and do some physics with this. So here we go. That's all the kit. So basically, this is how you do it. You sort of trap a number of coils here. So I'm exposing 25 coils in this case. And you'll gradually unravel your slinky as you go. And then you'll measure the length of your slinky with your ruler here to the nearest millimeter, ideally. So the idea is to measure the length of the hung slinky versus the number of coils N that are freely hanging from the desk. Now, in terms of, this is not just talking about physics and experiments. The actual presentation itself is a computational project. All right. So you notice that, I've used my smartphone to take a whole bunch of photographs of this. And to be honest, I think this is a real revelation. We can use our various cheap cameras to capture the physics that we do in the laboratory or at home. And then we can annotate that. I just use something like PowerPoint. It's very simple. But the clarity you get, the ability to get quality diagrams from photographs is a really good tip. That's not to say you shouldn't be drawing diagrams. Absolutely, that's utterly fundamental. But in terms of capturing, the reality of what you're doing, take lots of photographs and then get good at putting it into PowerPoint. So there we go. So what we're going to do is we're going to start with just one slinky under the coil, and then you're going to keep going. And I think I'm going to reduce it until about 11 are hanging freely. Otherwise, it's quite hard to measure beyond that. So there we go. How might you measure it? Well, we're going to sort of avoid parallax and all that kind of stuff, getting right to the bottom. So just squatting to look at the bottom of your slinky to find out where it is. And I reckon you can get the length of your slinky to the nearest millimetre. Okay. And so basically the height of the top is going to be where the coil kind of sort of extends from the table. So the ones above it aren't really under tension. So the slinky under tension is from the top of the table all the way to this bottom here. So that's a nice little activity. We're not going to actually do that today, but this would be a nice project to do if you have a few hours to while away. And then once we've got it, you can actually do a second experiment at the same time. So once you've exposed a number of coils, you can then sort of pull your slinky. About 5 centimeters is probably enough, and then you can record, say, 10 oscillations with your stopwatch. All right, so we're obviously going to get a bit of a timing error for this. So I've said, you might start and stop while observing the spring all the time. All right, so you need to sort of use your stopwatch without actually looking at it. So we might be able to ignore the random timing errors, and you can get away a single measurement for each end, but you might want to repeat that as well if you have time. And again, there will be a small systematic error because so it takes a little while for our brain to process what's going on. So there we go. That's the experimental setup. So there's a kind of Tao of doing experiments. And this is what I tell my students at Winchester, is that once we've kind of got an idea of our system, in this case, the slinky attached here, a number of coils exposed, we want to think about what kind of model, what things are we measuring, what physics are we assessing, and then work out a measurement system, which we typically use a spreadsheet for, and graphs that will plot themselves, set that all up, and then take some measurements. And that's a really good idea. That will take you a bit longer than just getting stuck in, but you'll know what range of measurements to take. From your graph plotting itself, you'll see whether you've got any errors. You'll see if your model is effective or not. So this is what we do. So there's a bit of a busy screen here, and I'll zoom in on the graphs. But this is basically a screenshot from the experimental setup that you'd start off with. So let's just going to go through what I've just mentioned. So number one, you're just going to set your experiment up. You can check you can extend the slinky 2 coils at a time, that works. Your book is heavy enough, that your full slinky doesn't hit the floor. So you don't want a slinky which is too long. So in other words, and just basically before you start making measurements, look at your slinky and press your smartphone. Just say when you're doing any experiment, there's a bit of play beforehand. What range of measurements are we taking? Can I take a measurement efficiently? Do I know what's going on, etc.? Is everything safe? Things going to fall off the desk, etc. All right. Now, before you start, you're going to set up a spreadsheet. So, we're not going to do anything really much harder than talk about spreadsheets today. And I just say this is a really good experimental habit to plot graphs as we go. And for those of you, who are a bit older, looking, sort of physics labs at university, you're often given a book, and that book doesn't leave the lab. All right. So setting things up, what are we going to plot, is what you do before you get started. Because sometimes experiments, once you've got going, you might have one shot at it. You might have expensive ingredients if it's sort of chemistry, something like this. So what am I going to do? I've got the number of coils, and I've gone, I think you can see that, 11 to 37. That seems like a decent number of data points. I'm going to work out the slinky length, and then I'm going to record 10 periods. I'm going to do it 3 times, because there's probably going to be some errors in there. And then what I can do is I can work out an average period, and then I can work out standard deviation in this, which will be pretty close to what I would deem as the error in that measurement. So as I mentioned, there's a model here, which is the slinky length goes as the square as the number of coils. So I can automatically have a model here, which is the number of coils squared. And there's also the square root of the length over the strength of gravity. So, looking at things like pendulums, if you think about that, the length over the strength of gravity, the units of that square rooted will give me a unit of time. So meters over meters per second squared, right? The meters cancel, and I end up with the square root of 1 over second squared, seconds to the minus 2 rather, and that will give me a unit of time. So from dimensional grounds only, our slinky period, for time for one oscillation, should be something like root L on G times some constant, right? Because there's nothing else really apart from the length and the strength of gravity. What's rather interesting is that there's no sort of elasticity of my system isn't really used as well, which is quite cool. So anyway, so what we've got is a kind of model where the slinky length goes as the number of coils squared. And we've got this model here for period versus length. And, I've put in some constants that I found earlier to work out this model. You may discover other constants empirically, which means by experiment. So what I've got is what I'm actually measuring, length versus number of coils. I've got that graph already plotted from my model here, and the period versus length. So those are the two things I'm measuring. But if we want to do some analysis, can you put in the chat what kind of graph must we plot if we want to sort of assess a model? I'll give you a few more sessions. There's only one type of graph that really we like for you to assess the validity of a model. What do we think? What's coming in the chat?
Straight line graph.
Absolutely, because a curve could be anything. All right. And I know we could say, okay, if I define this to be a quadratic, I can do a quadratic curve fit. But basically, we're looking to linearize a model. How do we get a straight line graph out of it? If it's straight, then there'll be a correlation with our model. And from the gradient and possibly the intercept of that, we can get the properties of the model. So that's basically one of the key tools of physics. So I've got L versus N squared, and I've got period versus the square root of L on G. And the idea is once we've taken some data, these will plot automatically based on these numbers here that we've got. So this is my model stuff to make these nice smooth curves. Notice I've got a smaller difference in N to make these curves nice and smooth. But essentially, as I make these measurements of the slinky length and the period, these graphs are going to plot itself. So that might take a little while to set up, but once it's happening, as you take the experimental data, the graphs will manifest as you go. That's quite good because if you get any anomalies, you can see them straight away. Okay, so that's kind of the top tip. Everything in one place, and you can write on your spreadsheet too with your model, so everything is there. There's nothing obfuscated. So here we go. This is this is the set of measurements that I took. So there we go. This is in 2022. So I don't know if you can sort of see my slinky lengths. I did 3 measurements of slinky periods, and I've used the mean and the standard deviation for this. So the standard deviation is pretty small. So in this particular case, I'm not really going to plot error bars on my graph. Though I will show you an experiment later where actually they're a bit more significant. So what we've got, so let's look at our analysis first. So L versus N squared looks pretty straight. And in fact, the R squared value, which is called the product moment correlation coefficient, which if you do look in the notes for today's session, I'm probably not going to use them to be honest, but there's a derivation in that of all of line of best fit. So you will probably do this in maths, you do a maths course, but essentially this number is related to how straight my line of best fit, which is the red line, is to my data. If R squared was 1, all the data points would exactly line up on my red line. Okay, so it's not quite as good as that, but that's a pretty strong correlation. And in fact, it's even stronger for period versus square root L on G. So I've got the idea, and what I've done is I've done a y equals mx fit. So I've said, right, my model, the slinky length for 0 coils is 0. So unless I believe there's some systematic offset, all right, and I think that's going to be small for this, then we can have a y equals mx fit. So basically all we're trying to work out is what the gradient of that line is. And then that's something we can use to find the constants, beta, as L is beta n squared, that's our model, and alpha, and that's the constant proportionality between root L on G and the period. So there we go. So for this particular slinky, beta is 0.0439. That's in centimeters in terms of our units. And the period is 4.9814. That's probably rather too many significant figures actually, because I think we probably got 4 there actually. So that's probably okay. No, we need to got 1. So that should be 4.981 really. Okay, so there we are. So our trend line, the correlation means our model is pretty reasonable. We can't prove it's true, but it's reasonable. It's got a quantitative correlation to it. Then our gradient is something we can then use to fit our data. All right, so what I've done is I have used beta to work out my model L equals beta n squared. So I've used that from the data, and that is plotting that red line here. Sorry, this one, the one at the top, the sort of quadratic. And so inside this sort of formula in this Excel sheet is exactly that model encoded. All right. So this is rather nice. So I kind of think the analysis graphs are what you need to do the physics. But actually, what's really useful is to have the data underlaid with your model. So it's almost like a summary, and you can really visually see that we've got some sort of smooth, ideally smooth curve underlaying our data. So I think that's kind of the minimum really to in terms of data analysis and presentation. And then in your write-ups, you will obviously explain that. You can put it into papers as well, all sorts of things, depending on the, how much effort you want to put into it. So in summary, we've got all the data really clearly displayed, and an error calculation if it's appropriate. We've got a linearized graph, which gives us will tell us whether our model correlates to our data or not. And the gradient and possibly gradient and intercept of that we can use as empirical parameters to fit a model to underlay our data. And you can see how nicely they fit there. So in a nutshell, that is what we do pretty much for every experiment. So there we go. That's it in big. I think what I'll do is, if you're interested in the theory of what these things are, I will point you to this resource, and you can get a stiff cup of coffee and have a read of that. But there we go. All right. So that is the Slinky physics experiment. Before we do that, though, there's something very interesting about. There's lots of interesting things about Slinkies. But what do you see? Put this in the chat. See if we drop a Slinky. What is very strange about that? You might need to use a high-speed camera. What would you see if you dropped a Slinky? What would be odd? What's happening in the chat?
It seems like the bottom of the Slinky seems to be suspended.
Yes. So it seems like it's defying gravity. So this is really interesting. It's all to do with a kind of shock wave. So when you've released the top, it takes a little while for the Slinky at the bottom to have its tension released. So if I'm just going to skip to the end of this little presentation. So there's a very nice video by some guy called, I think they call themselves the Slow-Mo guys. They're quite good fun. They're quite amusing as well, and they all dress up in lab coats. But there is some very serious physics here, although they're a bit they're very comedic in their presentation. But they use a very impressive, I think it's 1,000 frames per second camera. That's a bit more than I can afford, I'm afraid. But this is a screenshot from it, and you can see the bottom of the Slinky is completely unaffected from the fact that now the top has been dropped. So it takes a little while for the sort of wave of tension to catch up. Once it does, the bottom one falls just like anything else under gravity. So there we go. Where can we find this? So hopefully the link to Slinky Physics has been placed in the Q&A or the chat. If not, this is my website, the Eclecticon. So you go on the physics page and you click on experiments, and there's all sorts of stuff here. So what we'll be looking at is Slinky Physics. There's a YouTube video, and you can even download the Excel sheet. If you don't want to make it yourself, you can download that and then just change the numbers. And that might be, and your graphs will create themselves. So if there are any more general questions, so I've got a few other examples to show you before we release the challenge. Any questions in the chat?
Not at the moment.
Okay, fantastic. So here's an experiment I did today, which kind of illustrates pretty much what those sort of the things I've been talking about, basically. So let's just make that full screen. This is a really old school experiment. You can see my lab is also pretty old school as well, literally as well as figuratively at Winchester College. So what have we got? We've got some rulers that look like they're about to snap. So this is a cantilever. So again, I really recommend getting your cameras out. You may not be allowed smartphones in your school, but you probably might have laptops with cameras. And if you're doing things at home, you probably be allowed such things. So take some pictures of your kit, annotate them, and that's a really nice way of making things look real. Because sometimes sort of an abstract diagram doesn't capture all the details. Like, for example, this G clamp here, the bit at the top, you want to place that, upwards. Otherwise, it's really hard. It probably gets in the way for gas taps and things. So what have I got? I've got a G-clamp, and I've got a meter ruler, and I've got some weights as well to stick on the end. The G-clamp's probably going to be good enough. And what I'm doing is I'm loading it right at the end as far as I can go with up to about 1 kilogram. All right, don't go more than 1 kilogram, otherwise you'll snap your ruler. So I've also got another meter ruler, and that's mounted vertically using a good old, pretty ancient and well-worn retort stand with a boss and a clamp. So again, this is sort of physics basics here. All right, so what I'm going to do is I'm measuring the deflection of this ruler, the vertical deflection, and also I'm going to measure the width with a digital caliber, and these are the ones we've got. So these measure actually to 1/100th of a millimeter, which is rather cool. So I can measure the width and the thickness of this, and I can use a mass balance to work out the length, the mass. So again, what are we going to do? We're going to make a sort of spreadsheet and graphs that plot themselves before we do this. So what's going to happen? So let's just look at our measurement first. The key one really is our deflection. So what I reckon, this is why you have the vertical ruler here. So that's the deflection. And the way to do this is you can sort of mark on your ruler when there's no deflection. And then you can use a kind of Mark 1 eyeball and a 30 centimeter ruler to find the deflection itself. So you can work out sort of to the nearest millimeter where you are on the ruler that matches the bottom here. Okay, so again, squat down to avoid parallax, but this is how you do it. So, you could probably find that as if you looked at an experimental report or some instructions, you probably find there's something that says, well, take your measurements, avoid parallax, and you write that down. But what does it mean? Well, this is what it means. So take some pictures, and then, pictures worth several thousand words. All right. That's what avoiding parallax means. That's what taking a precise measurement means. There we go. I think that's my rather sort of nail-bitten thumb there. Anyway, so yes, note the ruler should be better aligned than in this photograph, indeed. So here we go. So we can measure the mass as well of the ruler and the widths and the thickness. So T, in some models which will soon come, is this one, 6.22 millimeters. The width is 27.75 millimeters. My mass is 114 grams, and the length is, to the nearest millimeter, 1,000 millimeters. So all good so far. Let's see what the model says. So there are two kind of sensible experiments you might want to do. This one's the simplest. To say, okay, how does deflection depend on the mass of the load? So you keep the load at the same position. So, or rather, the length of my ruler from the G-clamp, let's look at that one. That length there is going to be 0.8 meters. So if we fix that for the moment, and then we gradually load it up with some masses. So most labs have masses in 100 gram or sort of little cylinders. So I've gone from 0 to 1 there. All right, this is the height on my ruler. And I've worked in my spreadsheet. I've literally configured. So the green things are what I measure. And in sort of my spreadsheet style, I like to color code it what you're actually measuring. And then I might have a different color coding for the things that you are calculating. All right, so it's really obvious what your inputs are. Okay, when you think about inputs, you're thinking about coding as well. But this is just taking data. So make it really, really obvious what you're doing. And again, I don't think we need to use much sort of error analysis here, because we can measure things to the nearest millimeter and the nearest sort of fraction of a kilogram. So there we go. So my deflection in meters is going to be the difference. So this one would be 871 minus 857. I'm going down, divided by 1,000. So there we go. That gives us my calculation. So you're probably not going to write that down. It's very easy to make an arithmetic error. What you're going to do is literally write down what you see, which is the height on my ruler. Okay, so make experimental data collection as cognitively easy as you possibly can. All right, hence set your spreadsheet up to do the maths for you. So I've also got a graph which plots itself. So this is loading kilograms versus deflection in meters. And my measurements are all these ones. Here's a line of best fit from the origin, which is 0.1563x. So that number will be important later, but we've got a very strong correlation. And look at that, 0.999. It's basically true. There we are. So that's the first experiment you might want to do. The second one is more interesting. And so this is from a fantastic book, the Cambridge Handbook of Physics Formulae, Doesn't sound like an exciting read, but this should be on everybody's desks. It's brilliant, by a gentleman called Mr. Wone. So on page 82, which I think is the sort of engineering stress and materials section, if you have a cantilever, which is our ruler in this case, clamped at one end, then the deflection goes as the cube of the length of ruler exposed. So it's a cubic. I'm not going to derive that, but that's a really interesting bit of physics to do. And what else does it involve? Well, the constant in front of it, we've got the weight, and we've got something called the Young's modulus. So can you, if you know what a Young's modulus is, can you type that in the chat, please?
That's the stress over strain.
Stress over strain. Good. So stress, force per unit area, same dimensions as pressure, but that's something that's a material property. All right. So that divided by the strain, the fractional increase in length. So this is, we can do this. This is a bulk property of material. It tells you how stiff things are. So ceramics will have a really high Young's modulus. Rubbers and elastomers will have a pretty low one. So we're trying to use this experiment to work out the Young's modulus of wood, which otherwise would be quite hard to do. We'd have to kind of somehow stretch the wood with really kind of dangerously large weights. Something might splinter and your ruler will be destroyed. Rulers are actually, wood is quite stiff. So by bending it, we can use this relationship to find something which would otherwise be quite tricky to work out. So what else have we got? We've got T, which is the thickness of my ruler, and W, which is going to be my width of my ruler. And so we've measured M, W, and T. G will take us 9.81 newtons per kilogram, and L is our variable. So I've done exactly the same thing. So I've got a load, but I've also, if you notice, I've got height with no load and height with load. And there is a bit of variation here because there will be a little bit of bend of my ruler as I move the pivot. So I move, if I just put this over here. So the ruler will have a bit of weight to it. Okay, so as I move that clamp, at the end of it will not be the same thing. So in other words, the weight of the ruler itself will cause a little bit of bend as it's exposed. So basically, I'm going to work out the deflection from that point. Otherwise, there'll be an error in my analysis. So I suppose you could have a model more sophisticated, which takes into account the center of mass of my ruler. You could maybe, one of my students did this today, actually move the mass somewhere else. So keeping the ruler the same length, moving where the load is. But I think you'll change your model a little bit as a result. So in terms of the simplicity of this, we're measuring a deflection due to the load. I guess we're kind of ignoring the ruler itself. So you ought to work out the deflection from where its starting point is. So hence for this particular experiment, if I just go up here, there we go. I've worked out the height on my vertical ruler where my ruler is to start off, and it goes from 870 to 849. And then once I've loaded up, what does that end up being? Okay, so there we go. So that's going for, I've got a load of 1 kilogram on the end, and my sort of length goes from 0.8 to 0.3. So a good amount of data. So if I cube that, and then I can work this out. So basically, before I do this though, if I plot deflection versus L cubed, I get a very good straight line graph. Again, an excellent correlation here. And so I can use the gradients of that to basically derive a model. Okay, so this curve here is literally 0.3093 times the cube of the length in meters. And that's you can sort of see the model underlaying this. So that's told me about the constant here. I've not sort of predicted it because, of course, we're using this experiment to try and measure what our unknown parameter is, the Young's modulus of wood. All right, so I haven't got a theoretical prediction of what that's going to be unless I know what that is. So this is an empirical result, but nonetheless, I can see that my deflection delta is proportional to the cube of my length. That's what this straight line graph shows me. Okay, so if I'm happy that that is a good correlation, this is a sensible model, I can then use my data to figure out the Young's modulus. So there's a bit of maths to do now. So hopefully you can sort of see this. And this sort of thing should be written right on your spreadsheet. But then here's my model here. So sigma is 0.3093 L cubed. So 0.3093 is going to be the mass times the strength of gravity, Young's modulus, width, and thickness cubed. So if I rearrange that and then stick in the numbers, making sure I convert everything into meters, etc., meter and newtons per kilogram, and I ended up getting about 4.8 times 10 to the 9 pascals. So this is a really large value. So to stretch it by a significant amount, in terms of pulling your wood, that's going to be quite a lot of force. So we can measure a very stiff material. And again, it's there's no real right answer here, because I don't know really what type of wood it's made of. It might be, sort of laminated and lacquered. But if you look things up, there's a reference there to, I don't know if I've got that one, engineeringtoolbox.com. There we go. Does this work? Excellent. Let's consent to this. So this is a nice website which gives you numbers for all sorts of things, density, modulus of elasticity, all sorts. And it says for wood, somewhere between about 3 and 10 gigapascals. So yeah, it's probably not mahogany. It's probably in the middle somewhere. So that's sensible. So I've got this sort of reality check of my data. So there we go. We've kind of followed a process there. And I've got one more example, which a lot of you will do for your A-level physics. Any questions before I come out of this? Any questions, Kimlan?
Nope.
Right. Okay. So I think what I'm saying is there is a bit of a pattern to how you might write up your things. Now, in your physics labs, you might have your teachers might say, okay, here's a worksheet, fill this in, or a workbook. Obviously, please do follow what they want. But if you have some freedom, I really recommend making a little PowerPoint presentation, because then everything is there. You can then transmit it. You can make a PDF, all that kind of stuff. So a PowerPoint plus an Excel sheet, I think, is a good way of writing up a physics experiment. Okay, so this is something that actually, can you pop in the chat if you have done this for your A-level physics so far? It's one of the PAG ones, the physics. What does it stand for? I probably ought to know this because I teach A-level physics. But anyway, if you do OCR, this is one of the PAGs that you have to do. I think pretty much everyone. So has anyone done gamma attenuation by lead? Has anyone been there and done it?
Everyone says no.
Oh, fantastic. Well, there we are. This is new. So basically, it kind of says it all, what we've got here. This is a Geiger-Muller tube behind my title. So this is a tube it's containing a noble gas, I think it's argon. And what we've got is a tiny radioactive source. Okay, and this is producing gamma rays. I think it's cobalt, I think. I'll have to have a look. And you can see, if you look carefully, the radioactivity symbol. So obviously you don't want to have that anywhere near your face, but we're talking a very, very low activity. But if you're sick form, you are allowed to use these sources under supervision, and they're kind of mounted in this little sort of cylinder, and there's a sort of plastic block there. So what we've got lots of lead here, all right, so I'm varying the thickness of lead between a fixed distance between my source and my detector. And this is a kind of half-life kind of experiment, except rather than half-life, the time taken for my source activity to decay by a factor of 2. Hopefully my gamma source will last for a long time. So what we're looking at is how much lead will result in my activity, my decays per second, reached here to drop by a factor of 2. All right. So are my gamma rays going to sort of make it through this lead? All right. And X half is the amount of lead which will basically make my count rate drop by a factor of 2. So absorbing some of those gamma rays. So what sort of kit we've got? So again, this is pretty old. You might see something hopefully a bit more modern in your physics labs. This is probably not something you'll have at home. So what have I got? I've got a counter here. And I think when I did this experiment, I took a bit of time over it. So I worked out how many counts in 100 seconds. And so for every thickness of lead, so I had 1, 2, 3, 4, 5, 6, 7, 8 sort of slightly differently thick bits of lead. So that was of 800 seconds. So this is a sort of meditative experiment. And this is the box where you store your sources. Here's some forceps for picking it up. So again, particularly because it's gamma rays, although the activity is very, very low, it's not something you want to put near your face. So there are going to be some health and safety rules to follow for all of this. And we've got a Geiger-Mullis tube here. And this is what we call a radiation board. It's basically a piece of wood with some holes in it, which allows you to line all this stuff up very nicely. And often you get these little pieces of wood where you can put your lead cylinders, that kind of thing. So everything's really easy to measure. It's really safe. The gamma rays are not, or anything, the radiation is not sort of anywhere near you. You can handle it perfectly. So, most schools will have this kind of setup. So there we go. And the key thing here is you want to make sure your separation is the same, because gamma rays will spread out, sort of R² law. So we want to make sure the source to detector separation is fixed. And what we're doing is we're just putting something in the middle of it, which is going to attenuate. And it's that thickness is what we're going to measure. So yeah, cobalt 60 is our radiation source. There might be others for pure gamma rays. Obviously, we want just gamma rays for this experiment, although with a bit of lead, any alpha and beta won't make it through anyway. But in terms of the sort of it's only 8 centimeters, so you might get a little bit of beta radiation. So a pure gamma source is recommended. Right, so here we go. This is our radiation buckets. So any teachers on the call, this is how we do it. So we have a big locked cupboard with all our sources. And yes, don't forget to sign in and out your sources. So this is how it works. So nothing ever gets lost. And the radiation sources go in the yellow bucket, and then we take them to classes, and then they go back in the bucket and back into the locked cupboard. So there we are. It's quite so. We found the most colourful bucket we could get our hands on. So there we go. That's our full set. It's about 77 millimeters. And there we go. So this is our source. This is how they're all labelled. And it's a big sort of lead line box, basically. There we are. That's how you remove it. So you can see if you've never done this before, nothing to be afraid of. You've got your little source there. It's a little sort of capsule. There's a sort of end to it, which you pick up with your forceps. And there we are. This is all loaded up. So there we are. So basically, although I've got a little bit of lead there, the idea is you want to have maybe 3 lots of 100 seconds without the source, and that will give you your background activity. And then basically you do how many counts per 100 seconds, all right, and then divide by 100 for each sort of thickness of lead. And so what are we going to do? We are going to create a spreadsheet and a model which plots itself. So here we go. This is what I did. So we've got lead thickness in millimeters, and I used my my digital calipers to do this between 0 and 76.54. And I've got the counts per 100 seconds in a nice table. I've got 3 of those. Obviously, this is a completely random process. We will expect some errors, some different deviations here. I can then take the background off, which are, so this is 29, 36, 41. So my mean background in counts per second is 0.353. And so I'm going to remove that from the average of this divided by 100. So that's my my mean activity for my thicknesses. And this is going to be the standard deviation in that. So what we can do is we can plot a graph with some error bars. So if you look carefully, there's the plot that I've used is a crosshair. So the horizontal extent you can ignore that. The lead thickness is my errors are too small to see on this graph. So really it's the vertical error bars in the count rate. So my mean plus or minus my standard deviation. And this is a little bit of a battle in Excel, but I do have an eclecticon note how you can work out error bars, or you can follow a YouTube tutorial. But working how to plot error bars in Excel is a good thing for you to better do. So there we go. This is my data. You notice I've got one little anomaly here, but there's a decent range of error. My model is the red one, and I'll talk about how that's worked out in a moment. And to find out whether my model is going to work, I'm going to do the natural logarithm of my count rate versus thickness. And this will give me something from the gradient and the intercept to sort of set my model, which gives me these inputs, the half thickness and the initial activity, essentially, when my thickness is 0. So basically, you've probably done this before, but this is how you do it. So you say my activity is my activity without any gamma, any lead. and I'm going to divide that by 2 to the number of how many half thicknesses I've got. So if x is the thickness of my lead and x half is my half thickness, x over x half is the number of half thicknesses. So that's a number of times I divide my count rate by 2. All right, so we don't have to use the natural exponential for these kind of decay curves. Any power law is all right, and in some ways that's a little bit easier to think about, I think. So that will look like this. Okay, so after x half, we'll divide our count rate by 2. And if we rearrange this, so bring the 2 over here, and then we take a natural logarithm, we can bring down the power and have the natural log of 2. And then we've got a log of a ratio, which is a difference in the logs. So what we end up having is log of my count rate is log of my count rate at 0 thickness minus something times x. So a straight line graph, the negative gradient. So if I work out my line of best fit, I can use that and equate that with my half thickness. So my half thickness is the log of 2 divided by the gradient of this graph, or the minus gradient of this graph. And the intercept will give me what A naught is, all right, which is 2.477 in this case. So that's now going to be a model which I can use to underlay my data. So there we go. In summary, this is how I'm sort of doing my analysis, and this is my sort of presented underlay of model with data. So essentially, we've done the same thing 3 times for the slinky, for my cantilever, for my radioactivity half thickness experiment. So completely different physics, but you can see the process is the same. Right. So time to release the challenge this year. Ooh. Right. Okay. So are there any questions, by the way, before we get stuck in?
No, still no.
Right. Excellent. So the challenge this year, what's it all about? This year, we're going to be looking at projectile motion. So something that all of you, it's one of the first things you do when you study mechanics. So basically, if you've not sort of heard how or not done the challenge before, this is how it works. So this is going to be on the BFO website. It will also be on my Eclecticon page as well. And there's going to be a sort of instruction sheet with, and there are 9 tasks with some possible extension opportunities. So what I'll do, let me just talk about sort of how it works, and I'll roughly go through some of the tasks, and then I'll field any questions you want. All right, so quite a lot of text here, so I'll just sort of talk through it. Full screen mode. So basically, it's going to run from now till sort of August 2024. I think the exact closing date will be on the website. So let's just say it's the first few weeks in August. So you've got loads of time. You can do this individually, or you can do it in pairs. And the output is a YouTube video, maximum length 2 minutes. And please don't record a 4-minute video and then speed it up. We don't like that. So, you know, it's quite a tough challenge to fit it into 2 minutes. And I did, if you've got 2 of you, have a minute each, something like that. And a good way of doing it is to upload to YouTube. Set this as unlisted with disabled comments. So if you've never done that before, that's quite good fun too. And there's lots of easy ways of making screencasts. I like Screencastify. I think there's sort of as a free version, and that's an add-on to Google Chrome. There's probably lots of other ways of doing screencasts. So what's the output? What can you get out of this? Well, there are bronze, silver, and gold certificates on offer. And there's also a bit of a competition that the very best golds, the top 5, get to go to the Royal Society with the round 1, and well, all the winners of the various BFO competitions. That's quite a prestigious thing. And we've had some absolutely amazing entries. So, you know, if you want to have a go at this, then we're looking for lots of extension work as well. But this is a project. You know, this is to try. This is not an exam. This is to try and inspire you to get stuck in and do some physics over a longer period of time. We don't care what kind of language you use, although I would probably use MATLAB or Python, but we've had all sorts. So you can use whatever tools you like, and we will give you all the information. So it's a computational challenge, and this document, so there we go, that talks about sort of screencastifying what to do. So what I'm going to do is all the maths, everything is defined, apart from possibly the extension opportunities. And the idea is that you can use that, interpret it, use it to build spreadsheets and ideally code. The first one is, so this might be the challenge number one. We might look at an Excel model of projectile motion. So I'm not going to go through in the maths here. That's something that most of you will have studied. And if there are things you've not met, you can have a look at in a close way at the recipe. But essentially, a model of projectile motion, we're throwing a ball from a certain height at a certain angle, and where that strikes the axis. Okay. If I was doing this in Excel, this is kind of how I would do it. So if you notice, I've got my inputs color coded, my launch angle, my launch speed, my launch height, the strength of gravity, and maybe a time step. All right. So I'm varying time in 0.02 seconds. I'm working out my velocities in X and Y, my speed, and my X and Y coordinates. And I'm using equations of constant acceleration motion to do this. And that will plot my graph. So this is a really good thing to do when you're doing physics, particularly in theory as well. Once you've kind of got your head around a theoretical model like the X versus X and Y versus time, plot it. Build yourself an Excel or a Python model. This is such a good way of really understanding what's going on and making predictions. And you can kind of pause your physics learning for a bit. So that's challenge one. That can be done in Excel. Challenge two, you can use the analytic model. So this is called the trajectory equation, and that's a nice thing to derive. So you can work out X versus Y versus X precisely now. And so I don't have time now on this. I've just got X and Y. Challenge number three, well, we might want to sort of hit a particular target, and there's some really interesting maths around this. You will end up having a direct path at minimum velocity and a high and a low ball path. So as long as you're bigger than this particular velocity here, so big X and big Y are my coordinates that I'm trying to strike with my projectile. This is all drag free. That's the strength of gravity. That's the minimum speed. So if you are at that speed, that's the grey trajectory. There's only one solution to this. But if you're faster than that, you've got two options for your angles: the lower angle, which is the orange one, and the higher angle, which is the blue one. And your ball will hit this target. So it's a really nice bit of maths. If you do sort of further, actually, I think probably in normal maths you will solve this too. But you can implement it in Excel. There we are. All the maths is here. I'll skip through that. So challenge four. This problem is an absolute classic. So if we fire a projectile at constant speed, there we go. There's one here, the blue one. Well, what angle maximizes the ground range? So here we go. If this was on the ground, a lot of you will probably know that that's 45 degrees. But it's not quite true if we're at a certain height. And interestingly, there's a formula for it. It's an inverse sine of 1 over 2 plus twice the ratio of the gravitational potential energy to the kinetic. Actually, no, sorry, 1 plus 2 plus the ratio of GPE to the kinetic energy. So that's why 2 would be GH over half U squared. That's rather interesting. Where does that come from? Turns out the derivation of that either can be a absolute horathon, which is trying to differentiate this expression and then maximize it. But there's a very, very cute way of doing this. So you can work through the notes, and if you want to write a little paper up on this in your own words, that's a nice thing to do. But anyway, you can just implement this if you want, and if you use this angle, that will give you the largest range possible for your trajectory at a set speed. So there we go. There's a bit of maths there. Right, 5. Something called the bounding parabola. So if you were to take a hose, all right, so firing water at a constant speed and then sort of moving the angle of elevation, you'll trace out a parabola. And that's this one, this purple one here. And all the other parabolae that we can think about kind of are inside this. All right, so this is the maximum range parabola. This is the sort of high and low ball ones, the blue and the green, that go through this red star there. All right. So all the parabolae that you've met so far, you can kind of put on one graph. So that's that one. So challenge 6, and there's all the maths for this. That's the actual value of the bounding parabola. And then a really nice thing to do, particularly if you like calculus, is to work out the length of this curve. So you can do that numerically, but actually you can actually do this. So there's a lot of maths in this, but it's really good fun. It turns out for, I think, the maximum R, it's 1.15 U squared on G. So there are some nice formulae for special cases that you can derive. There's something called the universal parabola constant, which is the log of 1 plus root 2 plus root 2, 2.296. So there we go. So you can indulge every mathematical whim by going through that. There's some code you can use as well. So to get the sort of silver and gold, we really want to see you doing some computer code. So this is MATLAB. The green is commentary, and the black is the sort of MATLAB code. If you've never coded before, I wouldn't worry about it so much, but that might give you some inspiration of how you might do it. But you can use any language you like. All right. So here you can see here that I've got a function, so something with inputs and outputs. In this case, it creates my trajectory. Challenge number 7 is a rather curious thing, which is about the range of the projectile from the launch point, and you plot that versus time. And interestingly, you actually get sort of some dips. It's not always the same. So there we go. That's a sort of curious little sort of fact. Challenge number 8. We're now going to go 2D. So we can animate now a projectile bouncing. And there we go. So it's not just a bouncing ball. It's a sort of bouncing ball that's thrown. So this one, not just a static graph, but something that maybe animates the projectile. Maybe does that in real time. Okay, that might be quite cool. So there we go. That might be an extension. You could create a video file as well. There are lots of ways of making this smooth. There we go. That's my sort of animation trajectory. There we go. That will be my code for it. And if you notice, I've got a kind of a while loop. So I update the position using constant acceleration motion. And if I have a bounce, I change my y velocity. So that's sort of how you would do this. Another one, probably the next thing to do is to actually incorporate air resistance. So if you do that, we can't work out the trajectory analytically. If you can sort of see, it's a bit small to see, but the blue curve is my no air resistance model, and my red one, which is not symmetric anymore, is my model with air resistance. So you want, and this could be nicely turned into an app, for example, or something where you can dynamically change the angles and the velocities. So here we go. So this is sort of my Excel model, but you could do this, it'd be a really good idea to do this in code. So for this one, we need a few other things. We need things like the drag coefficient, the density there, my cross-sectional area, the mass, and I'm working out Newton's second law to incorporate a drag force, which typically goes as the square of the speed. But what's interesting is, of course, it always opposes motion. So as you go on your parabola, the angle of your drag force will change. So hence why I've got a constant in front of it, which is proportional to the actual velocity itself. So there's lots of recipes here, a lot of discussion of drag coefficient, and this model incorporates constant acceleration motion. So that's something to have a work through. So that's the basics of it, starting from simple Excel all the way to MATLAB or Python code, animated stuff, maybe an app, and you can really go to town. So some of the best applications last year. So you might do something like this. This could be an app. There's a projectile simulation, maybe one on a smartphone. That might be really interesting. Where in my case, I've changed the parameters of sliders. Maybe you could use something which you drag your hands over it, and that will change the launch angle and launch speed. Calculate various things, so the titles automatically change. This is all sorts of stuff you can do. Could you maybe save a high quality picture for a report? Maybe one of these. So how about launching a projectile from a spinning planet? And now the strength of gravity varies with distance from the center of the planet. So that could be a nice thing to do. And you can maybe do texture map pictures of your planet, like the Earth, the Moon, etc., the Death Star. That might be quite good fun. And there we go. So there's loads of opportunities for extension here. You could write a paper. That could be quite nice. But ultimately, are these 9 challenges. So best of luck. Do we have any questions? I'll be happy to field.
What language did you build your app in?
So that was in MATLAB. Yeah, MATLAB's my kind of a language of choice. I used to be an engineer, and it's got math built in. The graph plotting is really, really good. It has a sort of an app building. So I think I built apps in C#. That was a bit nicer in terms of the interface, but how you can set things up is really quite easy in MATLAB. Python, there is, what's it called? Tkinter, I think, Tkinter, something like that. Yeah, I mean, Visual Studio is how you would do it for sort of Microsoft, but it's a massive program. I think it's a bit of overkill, really. You know, but there's, you know, we could definitely have an argument about what the right tools to use. You know, pick something that you've done before or you like, or you can get your hands on. So Python's free. MATLAB is pretty cheap. It's about £30, I think, for the student version. That's probably where I'd start. But some of you will already have, you know, great skills in these things. So, you know, JavaScript, that means you can run it in a browser. You know, the Android operating system for smartphones or iOS. There's loads of ways of doing this. But I think if you're getting stuck in terms of how do I plot a graph, or, you know, how do I define a vector, maybe you're using the wrong language. You know, use a language where those things are trivial. So that's part of the challenge to find out. Any more questions?
There's a few more now. Do we have to write a paper as well?
So no, I mean, this is it's completely up to you. However, if you want to have a crack at being in the top 5, that is going to be very competitive. So, you know, we're looking at for, you know, the best entries, and quite not all, but a lot of them last year wrote a little paper as well. But most of the very best entries had, you know, not just did all the challenges and more, but they wrote smartphone applications. Some made websites with all the solutions on them. You know, they used it as a vehicle to learn some really good presentation and science techniques. But if you're starting out thinking, no, there's no way, you know, I'm just getting to grips with physics and Excel, you know, absolutely, this will be a good thing for you to, you know, bronze would be great. So roughly speaking, if you've done some of the Excel ones, bronze. If you've started to do some programming, you'll probably will get a silver if you've done most of the tasks. To get a gold, I think you do all the tasks quite well. And then obviously it gets very competitive after that. So, you know, you get out of it, you know, what you want. Any more questions?
And is it one video per question or one video for all the questions?
Oh, right. No. This is one of the hard bits of it. Unless we at the moment it's 2 minutes, unless we decide to make it slightly bigger. But I think it's I think we'll keep it at 2 minutes unless we say otherwise, and we'll make that decision very soon. You know, 2 minutes for the lot. So you have to describe how you've done it. So, you know, it's not going through all the details. It's just explaining what you've done, showing us how you've done the challenges. And, you know, you could show a bit of code, and there are some videos on the BIFA website. Actually, we should. I won't play them over this line, but you can have a look yourself. So if we go to so BP, actually, I'll go via the Eclecticon cut. So that'd be a nice way of doing it. There we go. So if I go to physics, go to courses, BIFO Computational Challenge. So all the challenge will appear here. And if you click on the BIFO website link, there we go. So Computational Challenge. And so we'll have the recording for this up soon. And if you scroll down, there's also a book which you might be interested in. And these are the gold entries from August 2022. Yeah, there's all sorts of stuff. I think my favourite was perhaps this one, the Leica conference reports. So Jamie Whiting and Nicholas Gregory, that was amazing. All 5 were absolutely superb. So you can see there was an app which was customizable from Maddie Bailey. V. Badham made a really good website. Mr. Brabham Renard did a sort of website and a custom planet for this one. So this challenge was looking at pressure versus altitude. Yeah, they looked at Mars or Venus or all sorts of things. These guys, Mariam and Ahmed, they did a phone app as well for different planets and different gases. So, you know, if you want to sort of see what the art of the possible is, have a look at those YouTube videos and see if you can make it even better. Any more questions?
Do we have to verbally explain our solutions, or would an annotated video be acceptable?
I think we want to hear your voice, actually. Yeah, I mean, as I say, it's the presentation part is quite key, because if you think about it, if you're, you know, presenting some physics, you know, in your research or at university or at school or in the real world, particularly in the real world, as an engineer or physicist employed in industry, you'll probably not get very much time to articulate what you're doing. And this is very difficult. If you've spent 2 to 5 years or more, researching your PhD, you think, Christ, I need hours to describe this. But actually, if you can describe the actual core of what you're doing in 30 seconds, 60 seconds, 2 minutes maybe, and get the key messages across and figure out what those are, that's a really useful skill, because often you'll be applying for money, for grants, trying to convince people to invest in you. So you need to gather those sort of précis and skills and those presentation skills. So that's kind of part of what the challenge is preparing you to do. So yes, we'd like to hear from you. We did have some students last year who wrote some music. I think that might be a bit beyond the call of duty, but we are looking for sort of novel ways of presenting, as long as you cover the tasks. Any more questions?
I think that's all for now.
Brilliant. Well, best of luck, everybody. So we've got a few more sessions. I think we'll talk a bit about chaos theory next time. And our last session, like last year, we will round off with a bit of epidemiology. So how we're using physics and maths to model viruses and infections, which obviously has been one of the major issues of the last sort of 5 years. So see you next time. And look at the website. The challenge will be formally released very soon. Thank you very much.